This video is on the limits at infinity. Limits at infinity has some stuff that it needs to get memorized. So all these basic limits at infinity, again, this just means that these are n behaviors. So if you look at the graph of 1 over x, looks something like this. Those are asymptotes, believe it or not. Is that these are infinitely, whether you go right or left, always going to 0. Okay, here's a brand new one. This is a fun one. We're gonna get, this is always gonna equal e. Now they might throw around some stuff where they might change up this right here or that right there, in which case they'll change up the answer a little bit, but we'll get to some examples about that. And then knowing the graph of arctan also is important, that the left end behavior of arctan is negative pi over 2, and then the right end behavior of it is pi over 2. Okay, and then here's some technical definitions about the vertical and horizontal asymptotes. Okay, so you've seen those before, and you can find them if you look at rational functions, but this is technically what it is. So the line x equals a is the vertical asymptote if and only if one of these two happens. This is an or. So if it goes from the left of that point equals positive or negative infinity, or if it goes from the right. This is actually supposed to be a plus sign on your notes. Hopefully it's more clear. Okay. Zoom in a little bit for you on that one. Okay. And then for horizontal asymptote, it's going to be the line y equals a if one of these things happen. So again, if the end behavior is at that value, whether it is right or it is left. Again, just one of those two needs to happen. Okay, another important thing is knowing how fast some of these functions are growing. So this is just a list of functions, and it's in order from growing slowest to fastest. So this is the slowest growing, and then you get just that, and it keeps going, and then the fastest growing function is x to the x. This is important to know because that will help us find some of these functions, or find some of these limits and their end behaviors. For instance, if you have something that's faster growing on the bottom of a limit going to infinity, you're going to get 0. But if something is growing faster on the top, you're going to get infinity. Okay? So those are good things to know. See, those are things all that need to get memorized. And now let's go through and apply these. So, for the first one, we're looking at the limit as x goes to either positive or negative infinity. It's not going to matter. For this one, you need to multiply it by 1 over the highest power. So the highest power for both of these is actually going to be 1 over x. So I'm going to multiply this bottom one by 1 over x, and that's all of it. Okay, I also multiply this by 1 over x. But if I do that, I'm going to have a problem because it's the square root. So I'll multiply this by 1 over root x squared. Okay, this is the same thing as this one right here. 1 over root x squared is the same thing as 1 over x. So what this enables us to do is to actually get that, push that in there. So the top is going to be x squared over x squared plus 2 over x squared all over 3x over x minus 6 over x. So what's going to happen here is cancel, if you can, with some of those x's. So plus or minus infinity. I'm going to get root 1, 2 over x squared all over 3 minus 6 over x. I just canceled out those x's there and those x squareds right there. Now we can start to zero some of these things out, like 2 over x squared. Well, x squared grows faster than 2, so that's going to get a 0. And same thing right here. You have a constant over x. It's just going to turn into 0. So what happens now is those are zeroed out. And you're going to get an answer of root 1 over 3, which is just 1 over 3. Okay. Next example this is that fun one that we saw before. Kind of sort of looks like that formula, the one that's the E. Okay, but what changes is we have this right here. So how this is going to change is this is going to equal, this is usually equal e to the 1, but that's going to make that a 1/2. Okay, which is root e. I'm going to rewrite this little part right here so it looks a little bit more obvious. So it's 1/2 times 1/x. So just look at that coefficient right there is always going to be your exponent. Okay. Next example. This one looks just like the first one we did, except it's a little bit nicer because there's no square roots. So the highest power on the top and bottom is going to be 1/x. So multiplying top and bottom by 1/x. This is going to give me 3x over x plus 5/x all over 6x over x minus 8/x. So these are going to cancel out right there. And these are going to zero out right there. Again, because x is growing faster on the bottom. So I'm going to be left with 3/6, which is equal to 1/2. Look at the next example. We have the limit as x is going to infinity of 2 to the x over 2x factorial. So this is one of those where we have to see which one is actually growing faster, and that will help us out. So if you look here, and if you're still a little confused, you can pull this up from the previous one. Well, 2 to the x would be right here, and x factorial is right here. So which one's growing faster? The x factorial, and it's on the bottom. So if it's growing faster on the bottom, you're just going to get a 0. I do want to add in an example real quick. Now I add this in because I think it gets a little confusing about these two examples I did here and here. Okay, so what you want to do here, these are growing at the same rate, so it's not 0. Like this one right here was just growing faster on the bottom. Okay, these are growing at the same rate. I know there's a 2 down there, but it's the actual function itself. It's growing at the same rate, top and bottom. So I want to multiply by 1 over that rate. Okay, so that's going to give me e to the x over e to the x plus 1 over e to the x all over 2e to the x over e to the x minus 4 over e to the x. So what's going to end up happening here is you're going to get a 1 on top, 1 plus 0, because those ones cancel out, all over 2 minus 0. So you get the answer of 1/2. Okay, so again, I made up that example just to show you that it works for more than just x squareds and x's. Alright, now let's find the vertical asymptotes using the definition. So by looking at this, you should know what the vertical asymptotes are. It's a rational function. What you do is you look at set the bottom equal to 0, and you're going to get x to equal plus and minus 1. Okay? So what I'm going to do to actually use the definition is I'm going to set a equal to plus or minus 1. So the limit as x approaches, I'll just start with 1, 1, you can pick the right or the left. It's not going to matter. I'll just do the right. Just for the sake of making this easy, I'm just going to define that as f of x. Okay? So this is going to be equal to, if you go from 1 to the right, this is going to equal, again, if you don't know 1 to the right, just plug in a 1.1. Because if you plug in a 1, you're going to get 3 over 0. Okay? So I can't have something over 0, so the answer is either undefined or positive infinity or negative infinity. So if just plug in a 1.1, if you do that, you're going to get 1.1 squared plus 2 times 1.1, which is positive, divided by 1.1 squared is a little bit bigger than 1, so I get positive on the bottom. So positive divided by positive is positive infinity. So I'm good. I just did a equals 1. Now I'm going to do a equals negative 1. And again, you can choose from the left or from the right. For giggles, I'll go left. And then you do the same thing. You just plug in a number that's slightly to the left of negative 1, which would be like negative 1.1. And then you could just plug those in. I'll save you time right here, and I don't want this video to be too long. You would get negative infinity. Okay, so your vertical asymptotes are x equals 1 and x equals negative 1. Last example is we have the limit as x approaches infinity of sine of x. Well, what do we know about the graph of sine of x? Goes on forever and ever. Does it ever change even when it gets to infinity? It does not. So this limit is not going to exist because it's just going to keep changing up and down and up and down. So kind of a lot to bite off here for limits at infinity, such as dividing by the highest power or the highest the function here, the fastest growing function. This is an E definition, brand new to you. This is the same thing as the first one, just a much easier example. Which one's growing faster? Same thing as the first example here, but we're just using a function of e to the x, using a definition, and just looking at end behavior. Okay, so that is going to wrap up our video for limits at infinity.